I should say like nonesimal, right? I don't know what a base 9 number system would be called that way, or sexesimal, or whatever. Septimal, octimal, decimal, decimal. For example, if we were in the base 3 number system and we had 1/3, which we'd actually have to represent, it would end up looking like this. This is going to be confusing. Never mind. Welcome to today's Math Minute. Good morning, good afternoon, good evening, good night, good whatever time it is where you are. Math Minute 42, I think, and I want to talk about 0.9 repeating. So I'm sure you've seen this before. 0.9 repeating, what is it equal to? Is it equal to 1? What's going on there? And there are basically 3 kinds of people in the world. There are people who are already aware of this, and they've made a decision already, whether they believe it or not. Then there are people who are going to see it for the first time, and once you kind of demonstrate why it is in fact equal to 1, they'll accept it and move on. And then there are the people who are vehemently opposed to the idea. They see your demonstration, and they have like a visceral reaction. No! 0.9 repeating cannot be equal to 1. So obviously I want to try to reach out to those people with that visceral reaction, and I want to try and give you some idea of why this could be mathematically true. But I also want to validate, I appreciate your skepticism. Because there are lots of things people do in math sometimes, like there's a particularly popular proof that you can do for middle school students, which is how I know about it, to show that 0 equals 1. And the reaction, no, that cannot be true, is absolutely the correct reaction. That's like watching a magician cut a lady in half and saying, no, that magician didn't cut that lady in half. There has to be some kind of trickery going on behind the scenes. So that instinct that sometimes mathematics shows counterintuitive things because those are actually not true things is a good instinct. The problem is that sometimes mathematics also shows counterintuitive things because sometimes counterintuitive things are true. And 0.9 repeating being the same as 1 is one of those counterintuitive but true things. To try and take some of the edge off though, let's not consider 0.9 repeating for a second. Let's consider 0.3 repeating. And I'm not going to do the thing where I say, oh, just take 3 of these and there you go. 0.9 repeating is the same thing as 3/3 is the same as 1. Although that is true. Instead, I want to try and talk through why people tend not to believe that something like 0.9 repeating is equal to 1. You have to make a distinction between the value of a number and the process by which we discern that value. The value of 1/3 is 1/3. It is the ratio 1 to 3. It is the fraction 1/3. And that is its value. There are a variety of ways we can represent that value though. And normally the first way that you encounter this is that you do some form of long division. You say, well, hold on, 1 divided by 3, that's something that we can represent as a long division process. We can say, how many times does 3 go into 1? And obviously the answer is it doesn't go in at all, so we add a bunch of zeros and we divide. We bring our decimal up here, we say 3 again does not go into 1, so 0 times 3 is 0, 1 minus 0 is 1, bring down the 0, how many times does 3 go into 10? That answer is 3. 3 times 3 is 9, and then we repeat the process. And of course, what we notice very quickly is precisely that this process will repeat over and over again. Every time we do another, 3 goes into 10, 3 times. 3 times 3 is 9. It's going to leave a remainder of 1. And so we think to ourselves, oh, okay, well, that's fair enough. If this is just going to go on forever and ever, we don't actually want to sit here and just repeatedly write down these 1s and 3s and 10s, 1s and 3s and 10s over and over again. So instead, we're going to give this a symbol. We're going to say, oh, this kind of repeating process we're going to represent as 0.3 repeating, where we've got that bar and we say, therefore, that's that. But of course, that's not that. It's not like there's a little gnome somewhere who is sitting around and continuing to write 3s because we've written that bar. Anytime we stop this process, we end up with something that is not equal to 1/3. Obviously, if we had just stopped this process right away at the first 0.3, 0.3 is not 1/3, it's actually 3/10. If we had stopped after the second 3, 0.33 is not 1/3, it's 33/100ths, or, and here's the insight we're going to need, 3/10 plus 3/100ths. The only reason that this ends up being a repeating decimal has to do with why we're calling it a decimal at all. This is a repeating decimal in the decimal number system, but it wouldn't be a repeating decimal in some other number system. For example, if we're in the base 3 number system, 1/3 is actually the same thing as what looks to us like 0.1, period. It's a terminating decimal in a base 3 number system. And that's actually the key. What we mean when we say that 1/3 is this repeating decimal 0.33 3, on and on forever, is that when we try to represent it in a base 10 number system, in the decimal number system, 1/3 ends up being the same thing as a particular series that goes on forever and ever. 3/10, that's the first 3, plus 3/100, that's the second 3, plus 3/1000, plus 3/10,000, and so on. But there's no special reason we have to use an infinite series like this to represent a sum of 1/3. We could just as easily say 1/3 is equal to 1/6 plus 1/6. And in fact, in a base 6 number system, this is precisely what it ends up looking like. 1/3 is the same thing as 0.2 in your base 6 system. In fact, of course, there's nothing special about base 6 either. We could represent 1/3 as the sum of 1/9 plus 1/9 plus 1/9, or another way to put it is 3/9 or 0.3 in a base 9 number system. You can represent any rational number in some base where it will terminate, or in some base where it will not terminate. It depends entirely on whether or not that rational number is a factor of the base that you're converting it into. When 3 is a factor of 9 or 3 is a factor of 6, yes, you're going to be able to represent that as a terminating decimal in that base. I mean, I shouldn't say decimal, I should say like non-decimal, right? I don't know what a base 9 number system would be called that way, or sexesimal or whatever, septimal, octimal, decimal, decimal. But for any base number system where 3 is not a factor of that base, like our own decimal number system, since 3 does not go into 10 evenly, in fact, since it shares no factors with 10 whatsoever, any fraction in terms of thirds will have to repeat, will have to be this kind of infinite sum in that decimal number system. There are some specific rules for what you're supposed to do to deal with situations like this. You encounter them in calculus when you start to look at what does it mean to sum an infinite series. Not a series that actually ends at some point, but that technically goes on forever, that little gnome keeps writing down over and over again. And that rule, if you have something where the ratio, the number you're multiplying by over and over again, like with 3/10, 3/100, 3/1000, 3/10,000, and so on, you can see that those bases are getting bigger by a factor of 10 each time. That's just a different way to say, oh, our ratio is 1/10. Each new term is 1/10 as much as it was a moment ago. That rule says you're supposed to take the initial value, basically the first partial sum or the first term in the series. In this particular case, that means that we would take a equals 3/10, and you're supposed to divide by 1 minus that ratio that you're multiplying by over and over again. So we would take 3/10 as a numerator and then go ahead and divide that by 1 minus 1/10, and you can tell that what happens there is we end up with 3/10 over 9/10, which in fact ends up simplifying to 3 over 9 or 1/3. So that infinite series of 3/10, 3/100, 3/1000, and so on, which is what we mean by 0.3 repeating, ends up being the same thing as the rational number, the fraction or ratio, 1/3. We can represent our infinite series for 9s in the same way. You start at 9/10, and then you add on 9/100 and 9/1000 and 9/10,000. I think I skipped something in there, over and over again, right? But you're just basically going to represent every place value in the decimal number system with a 9 over that particular denominator. If we plug that back into our same formula, you can tell we get 9/10 divided by 1 minus 1/10, which in this case happens to give us 9/10 over itself. And so that's the sense in which we mean the repeating decimal 0.99999 on and on forever is actually the same as 1. In any case, I don't harbor any illusions that I'm going to convince the hardcore skeptics, but why don't you comment down below and you can let me know, is this a different way than you've thought about it before? Is it helpful, this distinction between the value of a number and the process that derives that value? I hope so. Like and subscribe if so. If not, like and subscribe anyway. If there's something you want to learn about math-wise and I can be of service, please let me know. Otherwise, I will see y'all next time.